a quarter of a circle, a quadrant. On its two straight sides, we've drawn two semicircles facing inwards. Notice how they create two distinct regions. This curved lens where they overlap, let's call that area A, and this lonely petal in the corner, let's call that B. Your mission, prove that area A equals area B. Before we solve it, I want you to feel the puzzle. Look at A and B. Could one be larger? How might they be connected? I'll give you 5 seconds to make a prediction. Trust your intuition. Pause here and try to solve it yourself first. Now, let's see the truth. If calculating A and B directly seems messy, you're right. Here's a better path. Instead of looking at the pieces, compare the stage to the actors. What is the total area of the two semicircles compared to the quadrant? First, let's label our main character, the quadrant. Let its radius be capital R. So, its area is 1/4 of a full circle. Area quadrant equals 1/4 times pi times r squared. Now, meet our two supporting actors, the semicircles. Their diameter is r, so their radius is r divided by 2. The area of one semicircle is 1/2 pi times radius squared. 1/2 times pi times r divided by 2 squared. Simplifying r over 2 squared gives r squared over 4, so we get 1/2 times pi times r squared over 4 equals 1/8 times pi times r squared. Since the two semicircles are identical, their combined area is simply 2 times this amount. 2 times 1/8 times pi times r squared equals 1/4 times pi times r squared. Now, watch this carefully. This is the magic. The area of the two semicircles, 1/4 pi r squared, is exactly equal to the area of the large quadrant, which is also 1/4 pi r squared. But if their total areas are equal, why don't they look the same? Let's see what happens when we try to fit the two semicircles into the quadrant. When we add the two semicircles together, they don't fit perfectly. They double cover the lens-shaped region A, and they completely miss the petal-shaped region B. So we can write this as a story. The area of the quadrant equals the area of the first semicircle plus the area of the second semicircle, but then we must fix the double counting and the gap. We subtract the double counted area A and we add the missing area B. So our final equation is quadrant equals first semicircle plus second semicircle plus B minus A. Now we plug in the numbers. We know the quadrant and semi-1 plus semi-2 are both 1/4 pi r squared. So 1/4 pi r squared equals 1/4 pi r squared plus b minus a. Subtract 1/4 pi r squared from both sides, and we are left with 0 equals b minus a. Therefore, a equals b. The puzzle is solved. And there it is. The shapes that looked so different are mathematical equals. The true lesson here is powerful. Often the relationship between the whole and its parts is more important than the parts themselves. Look for the bigger picture and the answer will often reveal itself. If you enjoyed unraveling this mathematical mystery with us, hit the like button and subscribe for more deep dives into math and science. Let us know in the comments what other puzzles we should explore next. Thanks for watching.